Hello, students. So, before I actually get into the meat of this lecture, let me tell you why I'm doing what I'm doing. So some of you may know, I don't know if I've dropped this bit of knowledge in general. I am right now not a US citizen. I'm a Canadian citizen with a US green card. And I'm in the process of applying for citizenship. And my citizenship test, things like the civics exam and the language exam, are on Thursday. And these things are very difficult to reschedule. It's in Minneapolis. And it seems like starting at about midnight tonight, the roads are going to be completely impassable. So I'm going to be probably canceling quite a few classes. I'll send out a formal email. But either way, I think it is useful to have some recorded videos. Either they'll be supplementary to the actual lectures in class, or they'll replace them. Cool. So this isn't actually the topic of today. First thing we need to do is there was one theorem that still needs to be done from last time. The fact that the limit of a sequence is unique. And it's kind of implicit in the notation we use, right? In class, you write things like the limit of x sub n is equal to 0 if x sub n is a sequence that converges to 0. This equality makes it look like, oh, well, this limit of xn is a single number. But that's not immediately apparent based on the way the definition is written. All right, we say limit of xn is equal to L if for all epsilon bigger than 0, there exists a big N such that for all little n bigger than big N, absolute value of xn minus L is less than epsilon. And so L has to be a number which satisfies some condition. There's no a priori, there's no thing at the beginning that makes it clear that there's only one number that satisfies this condition. Let's prove there's only one number that satisfies this condition. Let us prove, let xn be a sequence. Suppose that xn converges to L, meaning this condition holds, and xn converges to k, meaning this condition holds for k. Then those two numbers had better be the same. That's what uniqueness should mean. There's well, at most one limit. Not every sequence converges. Well, so we want to show that k is equal to L. And it seems like something really bad should happen if they're different. So let's suppose, for the sake of contradiction, that k does not equal to L. In particular, then, the absolute value of L minus k is positive. Right? Two numbers are different, they have positive distance between them. Now, let's see, I have this condition being true for both k and for L. For any positive number I want, there's a positive number that seems relevant to this problem. So let's try to use that positive number and see what we get out of it. So let's take epsilon to be absolute value of L minus k. Oh, I guess you could use k minus L if you think these things should be in alphabetical order, right? It won't make a difference. This will turn out to not be the correct epsilon. Fair warning. But we'll see why. So let's see, since xn converges to L, this thing follows. So we have something that's true for every epsilon. There's a particular choice of epsilon. Let's use that choice of epsilon. We know something's true for every epsilon, so we know that this something is true for any particular epsilon, like this one. So there exists some big N, such that if little n is bigger than big N, then absolute value of xn minus L is less than epsilon, which I'll go ahead and remind you is absolute value L minus k. Similarly, xn converges to k. So I can make this same statement, a different choice of big N, of course. This big N depends on the choice of epsilon, but it doesn't have to be the same big N for both of these situations. So there exists some other threshold number, big N prime, such that if little n is bigger than big N prime, then absolute value of xn minus k is less than epsilon, which is L minus k. So that means as soon as I take a little n that's bigger than this big N and bigger than that big N prime, then these two statements will follow. Fair enough. Well, how do you make a number bigger than two different numbers? Well, just make it bigger than whichever one of them is bigger. Let's take n double prime to be the max of n and n prime. So that n double prime is bigger than or equal to n, and n double prime is bigger than or equal to n prime. This will actually be a really common idea. If ever you're in a situation where you have two different choices of n prime, and you need little n to be bigger than both of them, just take little n to be bigger than the max of the two of them. That's a good way to be explicit. So let's let little n be bigger than big N double prime. Then let's see what happens. So let's see, as little n is bigger than big N double prime is bigger than or equal to big N, this implication holds. If little n is bigger than big N, which it is, then this conclusion happens. As little n is bigger than big N, absolute value of xn minus L is less than absolute L minus k. Similarly, as little n is bigger than big N double prime is bigger than or equal to big N prime, absolute value of xn minus k is less than absolute value of L minus k. So let's try to get an idea of what we can do with this. So I see two different inequalities, and I'd like to combine them maybe using some sort of triangle inequality argument. So let's try to do this. This will be a lot like what we did with negative 1 to the n. So I'm going to leave myself space here intentionally. Absolute value of xn minus L minus xn plus k. Let's study that. So that's the same thing as absolute value of xn minus L, and that's encouraging. We know that that's small. Minus, well, no, let's say it this way, plus k minus xn, which by the triangle inequality is less than or equal to absolute value of xn minus L plus absolute value of k minus xn. And on the one hand, in future lectures, I'll say, well, that's less than the absolute value of L minus k by this step, but maybe I'll add an extra step. So this is by the triangle inequality. That's equal to absolute value of xn minus L plus absolute value of xn minus k. And, well, let's see what we can say about this. That's now strictly less than. Xn minus L is less than the absolute value of L minus k, plus xn minus k is less than the absolute value of L minus k. That's 2 times L minus k. But let's look at what we started with. What is this the same as? That's the same thing as, well, I guess I didn't give myself enough space to do all of the arithmetic. That's the same thing as absolute value of L minus k. So I've just concluded that L minus k is less than 2 times L minus k. That's not a contradiction. Things usually get bigger when you multiply them by 2, especially if they're positive. So no contradiction. So that's kind of a bummer. But I kind of told you that this epsilon would just not be right. So where did these numbers come from? They came from that L minus k in absolute value. And remember, this L minus k, that could have been any fixed positive number. So now look at the result. What positive number would you want to put here underneath all of these pink lines so that L minus k is less than 2 times whatever is in that pink line is false? And I can think of 2 reasonable things to do. Well, if you want to divide everything by 2, you would wind up with L minus k is less than L minus k. Absolute value of L minus k is less than absolute value of L minus k, which is false, so you could do that. Maybe if you're the type who feels more novice, you could divide by 3. And then, well, you would then not need to know that this was a strict inequality. You would still get a contradiction if it's loose. But part of the point is, right, if you get to choose an epsilon. So I'll divide by 2. So I'll divide all of the L minus k in absolute values by 2. Fair enough. So let's just read through and impose the changes. Little n is bigger than big N, so absolute value of xn minus L is less than L minus k over 2. Absolute value of xn minus k is less than absolute value of L minus k over 2. So this is now less than L minus k over 2 plus L minus k over 2. That becomes 2 times absolute value of L minus k over 2 is absolute value of L minus k. Now let's see, do we get a contradiction? So I see that absolute value of L minus k is less than absolute value of L minus k. Yeah, that's a contradiction because they're the same. Let's see, did I give myself more space? I didn't. I'll use the space up here. Thus, as we conclude that absolute value of L minus k is less than L minus k, we have reached a contradiction. Full stop. So, whatever it is that we assume for the sake of contradiction must be false. So let's go back and trace down what our assumption for the sake of contradiction is. So for the sake of contradiction, we assume that k is not equal to L. So that must be false. So it must be that k equals L, as we claimed. Cool. All right, so thank you for putting up with this. I guess I didn't give you a choice, but thank you nonetheless. I'm going to hit stop now. This completes the lecture that we were supposed to finish last time. I'll go through now a lecture on limit laws. I'll be right back. Oh, goodness.